A planar lamina can be thought of as a thin sheet of uniform density, and we're going to identify that density as rho. And if we have such a planar lamina whose shape is a region in the xy plane between the x-axis and a function f of x, as x goes from a to b, then we have that the mass of the lamina is equal to rho, the density, times the area, the integral from a to b of f of x dx. And we'll refer to that as the total mass, even though we're not talking about a volume. And of course, this is a theoretical construct, but it's density times area, and so that result's going to give us mass. We can also consider moments. The moment about the y-axis is rho times the integral from a to b of x times f of x dx, and the moment about the x-axis, m sub x, is rho times the integral from a to b of 1/2 f of x squared dx. Using these formulas, we have that the center of mass is x bar y bar, and that is equal to, as before, m sub y over m sub x over m, the total mass in the denominator. Before we use these, we're going to justify these formulas for the moments. And to do that, we're going to consider a region in the xy plane. Our region is between the x-axis and this function f. X is going from a to b. And as we've seen so many times before, we're going to consider an incremental rectangle. We're going to consider a subinterval on the x-axis from x sub I minus 1 to x sub I. And within that subinterval, we're going to consider actually the midpoint. We'll call it x bar, and it is x sub I minus 1 plus x sub I over 2. Associated with that value is a height, and that height is going to be f of x bar. It should be x sub I bar. And so the area of the ith rectangle is f of x sub I bar times delta x, where delta x is, of course, the width of the rectangle. The center of mass of the ith subrectangle is exactly at the center of the rectangle, and so it should have an x-coordinate of x sub I bar and a y-coordinate of half the height, so 1/2 of x sub I bar. And you might take a moment to convince yourself that this is true. Now, the moment about the y-axis is going to be, well, mass times distance, as we saw before. And so a moment about the y-axis is going to be rho times x sub I bar times f of x sub I bar times delta x, where here x sub I bar is the distance from the y-axis, and f of x sub I bar times delta x, we already decided was the area. The area times the density gives us our mass, and then the distance portion is our x sub I bar. It's a little more complicated for the moment about the x-axis, but same ideas. Rho times the distance to the x-axis for the center of mass, and that is going to be 1/2 of the function height. So the center of mass here has a distance from the x-axis that is half of the height of the function value at that point, x sub I bar. And then we still need the area, f of x sub I bar times delta x. So the moment about the y-axis then becomes rho times 1/2 of f of x sub I bar squared, the 1/2 f of x sub I bar coming from the distance from the y-axis for the center of mass, and the other f of x sub I bar for the squared coming from the area. Oh, and let's not leave off our delta x. And these are, of course, incremental moments. Whoa, I called that second one m sub y. It's m sub x. These are incremental moments, and adding together a bunch of those incremental moments is where these integral formulas come from that we just talked about. Now let's look at an example. Here we're given a function y equals the square root of x, and then bounds y equals 0 and x equals 4. And we're asked to sketch the region given by the curves, estimate the centroid, which is the center of mass of the region, and then find exact coordinates of the centroid. Looking at this, we may be thinking, hey, there's no rho. What's the density? It's uniform density, and you'll see that in the integral for total mass, or in the expression for total mass, we have rho. For m sub y, the moment about the x-axis, we have rho again. And so when we divide m sub y divided by m, rho is actually going to divide out. And now you may be asking, what about if there was a variable mass? Hey, take Math 5C. At this point, what I would like for you to do is follow all of these directions. Sketch the region, estimate the center of mass, or the centroid, and then find the exact coordinates using the formulas that we've written down. Pause it, give it a shot, see what we get. Well, I hope that went well for you. I've sketched the region here, the square root function from 0 to 4, and our mass is rho times the integral from 0 to 4 of f of x dx. F is the square root of x, and so we end up with 2/3 rho x to the 3/2 by using the power rule. Evaluated from 0 to 4 gives us a mass of 16/3 rho. For the moment about the y-axis, we have rho times the integral from 0 to 4 of x times the square root of x dx. That, of course, is x to the 3/2. Using the power rule, we get that that integrates to 2/5 rho x to the 5/2 evaluated from 0 to 4. And that gives us a result of 64/5 rho. For the moment about the x-axis, we have the rho times the integral from 0 to 4 of 1/2 of the square root of x squared dx. That gives us 1/4 rho x squared evaluated from 0 to 4 by using, again, the power rule. And that evaluates to 4 rho. X bar is the x coordinate of the center of mass, the centroid, is m sub y over m. And so 64/5 divided by 16/3, that simplifies to 12/5. Finally, y bar, the y coordinate of the centroid, is the moment about the x-axis divided by m, and so 4 over 16/3 for 3/4. Looking at it visually, 12/5 is a little bit more than 2. 3/4 is, well, it's 3/4 for goodness sake. And so the center of mass turns out to be that point there. Finally, if we have a region between two curves, say f and g, x bar is going to be 1 divided by the area of the integral from a to b of x times f of x minus g of x dx. 1 over the area is just, it's what would happen if you divided by the mass and then the rows divided out, right? So you'd still need to compute the area, and you know how to do that based on the area between curves work that you did in first semester calculus. The integral here, though, it's x f of x minus x g of x with the x factored out, and so it's the difference between the two moments there, essentially, for the respective functions. For the moment about the y-axis, we again have this 1 over a. It's an integral from a to b of 1/2 of f of x squared minus g of x squared dx. And again, what we see is it's the difference of the moment about the y-axis for f and the moment about the y-axis for g.